How about some examples from business and industry? Again, no new definitions or rules or theorems here. We're just going to start like this. To optimize something means to maximize or minimize some aspect of it. For instance, we could ask a question and answer. What is the size of the most profitable production run? Or what is the least expensive shape for an oil can? Or what is the stiffest rectangular beam we can cut from a 12-inch log? We usually answer such questions by finding the greatest or smallest value of some function that we've used to model the situation, and that's what we're going to do on the next couple of examples. We start with fabricating a box. An open-top box is to be made by cutting congruent squares of a side length X from the corners of a 20 by 25 inch sheet of tin and bending up the sides. For those of you who can't see this visually, I'll try to draw. Here's a rectangular piece of, we'll call it tin here, and it is 25 inches in length and 20 inches in width. And what we're going to do is cut a square from each corner, an X by X square. So there are the drawings for my squares. And then we'll fold along those edges created. And that middle rectangle will be the bottom of the box, so that our box looks something like this. There's the front, there's the side, there's the back of the box, and there's a bit of the inside. So there's the box, and what we want to do is, I think eventually we're going to find the maximum volume of this box, interpret the meaning. Yeah, so that's what we're going to be doing here. I guess what we need to do first is write the volume of the box as a function of X. And we know that the volume of a rectangular prism is base times height, and then the third dimension times the depth, or whatever other words you want to use to come up with the volume here. So let's get into the measurements. I think it's pretty easy to see that since we're folding up these edges, the height of the box is going to be X. Then the long edge, the width, basically it started out as 25, but then we took off an X on either side. So let's call that 25 minus 2X. That would represent this length I'm dotting in blue. So using the same logic, the length of the width is going to be 20 minus 2X. So there's 20 minus 2X. So that makes our answer to part A, V of X, is equal to X times 20 minus 2X times 25 minus 2X. Great. What is the relevant domain of V of X is the next question, and that should be pretty easy to answer. Obviously, we want to have some kind of X cut here that is bigger than 0, because we want to be able to fold this 10 into a box. So we got to cut out at least something on the edges. And then as far as the max, we wouldn't want to go over 10, because if we happen to make a cut that was 10 or more inches in width, then we would be cutting, well, the whole paper. That would be 10, and we wouldn't have enough left to fold up a box. So the relevant domain here, let's go with 0 to 10. And I'm going to go ahead and close in that domain rather than making it open, so that we can use a candidate's test later on. The candidate's test, remember, we want to have a function that is continuous on a closed interval. Okay, next up, B. Find dV/dt. And then using appropriate units, interpret the meaning of dV/dt or dV/dx in the context below. So we want to find V prime, and I think in order to do that, rather than employ a product rule with another product rule embedded, it might be easier for us to multiply everything out here and then just use the power rule on the resulting polynomial. So I think that if we multiply everything out here, we're going to end up with a volume function that looks like this. It's going to be 4x cubed minus 90x squared plus 500x. So there's the volume, and that means for part B, V prime is going to look like this: a 12x squared minus a 180x plus 500. So what is the meaning of that? Well, it's the change in volume of the box dependent upon a change in the cut of x. So it's change in volume per change in cut of x. So let's move to C. Find the value of x that will maximize v of x and justify your answer. So let's find the critical value. We set this equal to 0 and solve, and I'm going to use the graphing calculator to do that. So let's see. I want to go into my apps button, and then I'm going to use Polysimul option 9 and the polynomial root finder. That's what I'm after here, the roots of this equation. So let's hit 1, and we want an order 2. That's a quadratic function, so let's hit next. And then we want to type in the coefficients. So the first coefficient is 12. We'll hit enter there. And then we want minus, we'll hit enter there. 180, well, let's try that, 180, hit enter there. And then plus, hit enter there, and 500, enter there. And let's hit solve, that would be F5. And there we have it. 3.6381 and 11.319. Those are the two critical values, but the second one doesn't really mean anything to us because we know that the relevant domain in this problem was 0 to 10. And if we made a cut of 11 by 11 on that square, we wouldn't have any 10 left over to form a box. So the one here we're interested in is 3.681. So let's say that x is equal to 3.681. Now, find the value that will maximize v of x and justify your answer. We're going to justify our answer with a candidates test. So let's set up an x v of x table. And we've got a left endpoint 0. We've got 3.681 as our critical number and then a right endpoint of 10. We know that the volume is going to be 0 if we plug in a 0 because that would involve it going right here and multiplying by 2 more factors. 0 times whatever is still 0. We also know that if we plug in a 10, v of 10, the volume is going to be 0 as well because plugging a 10 in next to this 2, 20 minus 20 would be 0, and the same thing would happen as did when we plugged in a 0. Now we want to know v of 3.681. So let's try that out. We're going to plug a 3.681 in here and in here and in 3.681 there. So let's grab our graphing calculator one more time. Let's go back to the home screen and quit that app. Let's go 3.681 times a 20 minus 2 times 3.681, and then times a 25 minus 2 times 3.681. Let's hit enter there. We get a volume of 820.528. 820.528. Now, we want to use appropriate units and interpret our answer in the context. So what have we done here? We found a volume. So this is 820 cubic inches. So there's that volume. Exercise 7 is one that's going to be left to you. This example 4, we're going to leave to class or on your own. I would say take a look at page 235 in your text. And this one, number 11, we're going to leave for class as well. So join us live on Google Meet or come see us live here at Heron High School, and we're going to work this design a tank problem together. That does it for this video.